Okay, this time should be okay, I think. Let me see, 10 minutes. Let's see back. I think they should be okay. Let me know otherwise. Okay, so here's the thing. Janildu, thanks for coming in, man. I really appreciate it. Okay, so what just happened? Basically, every once in a while, audio, video desync happens. I can't really fix that. So, if you were watching on YouTube, you probably missed the last 10 minutes of stream, but that's okay. We were covering what we were doing 10 minutes ago. So, let me just very quickly go back through that. Basically, the idea is we're talking about the Fourier transform one more time. And I will get to that in just a second, Avaze. What we're going to do is first talk about what the Fourier transform is. The idea is that we have some sort of big F in frequency space, and we have the transformation in with some real space function. And we kind of work between the frequency space and real space function with the Fourier transform and inverse Fourier transform here and there. Now, forgive me, that was kind of a messy line. Okay, now one way to make the Fourier transform fast, which is what the additional F in the Fourier transform stands for, we use the Cooley-Tukey algorithm, which, with the powers of recursion, takes an n-squared problem, which is pretty much intractable, and turns it into an n log n, which is quite nice as it scales higher. Okay, for 2 dimensions, it does about what you'd expect. We add an additional exponential to the sum up here, and those exponentials add together, and that's how we get a 2-dimensional FFT. From there, we started talking about the discrete Fourier transform. Let me see. During the last episode, it took like 1 minute max. Wait, what took 1 minute max? 1 second. Oh, the back online? Yeah, so here's the thing. Every once in a while, I have to restart my computer when the audio and video desync, and there isn't really much I can do about that. So, like, I actually do check every single morning when I get up to make sure the audio and video are set. However, today, I accidentally woke up late. Forgive me, it's 5:30 in the morning, and woke up late, and that was the issue. Sorry about that. Now, what we can do is we can split the Fourier transform into real and imaginary components, and this is very important because this allows us to, how do I put this? Basically do different transformations that people can use for different reasons. Now, to answer your question, Avaze, during the last episode, you said that you need an FFT for your work. What exactly do you do with it? I only use it so far for solving differential equations. That's actually exactly what we're doing. So, let me see, where is my pen? There it is. If we do page, new page before. What I do for my work is I solve the, well, Schrodinger equation. Equation using what's known as the split step method. 1 second, method. Okay, to do this, let's go ahead and do page, new page before. How do I put this? Okay, the Schrodinger equation has parts of it that are both real and imaginary. So the idea is this: we have, let's see, 1 over. You can also use it for filtering signals. Exactly, and that's one of the things we want to talk about today. The FFT is a glorious invention, in my opinion. Okay, so let's see. The Schrodinger equation. Yeah, it's actually really cool, the Schrodinger equation. It's one of those things that, like, at first you're not going to get it, and then you kind of sort of start to get it, and then you start to realize you didn't get it. It's great, it's great. So we're going to say, oh gosh, I don't remember the constants. We have d phi over dt. Is going to be equal to, let's see, we're going to have h bar squared over 2m del plus v naught, some sort of potential over there, and let's see, I guess it's h over I, something like that. I feel like I got the constants wrong. These are bars. This v is some sort of harmonic potential, so we could say, like, I don't know, for example, x squared plus y squared with some sort of omega out front. Shoot, did I get the constants wrong? Let's see, there's a negative out here. That's it, there's a negative out there. Okay, so what we can do is we can split this up into real and imaginary components. 1 second. There has to be an h bar over I somewhere in here. This, I think, is an h bar over I squared. Yeah, it has to be. So this is going to be our momentum component here, which is P. and this is going to be our, well, non-momentum component, which is x. And the idea is we can solve this particular equation by going back and forth to momentum space and multiplying the wave function by it. So we take our wave function, we put it into momentum space with an FFT, and then we multiply this by our momentum space guy, so here. Then we use an IFFT to bring it back into real space and multiply it by this guy here. Our x, essentially. And something like that. So we hop back and forth. I'm terrified that I got these constants wrong. Is there, what is this? The nabla is squared? Yes, the nabla is squared. Gosh, as someone who uses this literally every day for work, I have totally forgotten all of the extra everything around it. I apologize for that. Lawrence, hey, thanks for coming in. Yeah, it's a Laplacian, definitely. Okay. But anyway, the idea is that we solve this equation by hopping back and forth from real space to imaginary space, and that's how we do it. Again, it's called the split step method. We use it a lot for work. It's pretty interesting. Now, what exactly do I want to talk about here? It's not really related to that. In fact, I want to try to do different things for the first hour, and then around 6:10 in the morning, which is 30 minutes from now, I want to kind of switch gears to something a little bit different, which should be interesting to a lot of people. However, I don't know how interesting it's going to be. I've got the feeling that some of you guys will be into it, some of you guys won't be. I personally find it incredibly cool, but we have to introduce a lot of concepts for how these transformations work first, before going from there. So, one more thing I want to point out, since we've already mentioned the discrete cosine transformation, there's also a discrete sine transformation. However, we'll not be probably looking into this episode. The discrete sine transformation is about what you'd expect. It is, let me see here, big X of k. And again, forgive me for messing around with notation here. I'm kind of assuming you can kind of go back and forth, but you'll see it notated in a bunch of different ways in a bunch of different areas. It's going to equal the sum of n equals 0 to big N, little x of n, again position space, of sine of pi over n plus 1, n plus 1, k plus 1. Okay, so this is basically, and I think there's an I out here. Oh, no, this is the imaginary component here. So we have the imaginary component of the Fourier transform. And again, when I write FT, Fourier transform, I always put an F in front of it just because, I don't know, FT is kind of weird to write down. I don't know why, but when I say FFT, I also mean Fourier transform, discrete Fourier transform in particular. Okay, so now let's just go ahead and mess with the code a little bit. We have, hey Gusterwin, we have a lot of things that I want to try here and there, and a lot of things that I think will be interesting to you guys. We left off last time with a code that was not quite working. So let me also describe exactly how we fixed that code up, and say that it is available now on github.com, and to the best of my knowledge is working perfectly fine. Oh, that wasn't what I wanted to do. Bring that over there, copy that over. Okay, so now we're going to cd into projects, Simuleos, and FFT. That was FTT, FFT. CD projects, Simuleos, and FFT. Okay, let me go ahead and ls here, and let's open up FFT slow. Okay, here's the issue. The link that I gave you guys, which is what I was kind of following to go from what we needed to do, basically split the Cooley-Tukey algorithm into evens and odds, and we did the Cooley-Tukey algorithm again and again and again and again with all the evens and odds. However, in Julia, counting starts at 1, right? So I had two different phrases down here. Let me just go ahead and put down what I think I remember I had down. I think these guys were switched. So I think we had 2 to n up here and 1 to n down here. So the even was going from 2, 4, 6, 8, 10, so on and so forth, and the odd was going 1, 3, 5, 7, 9. However, because of the way Julia counts and because of the way Python counts, all of their evens were my odds and my evens were their odds, if that makes sense. So it was basically an off by 1 error, but the off by 1 error propagated through every single element in the code. So just simply by switching those up, we had everything fixed. So now this works perfectly well. Today we're going to be working with Julia again, and we're going to be kind of using some features to make it a little bit easier to describe exactly how the FFT is working. Now obviously you can do this in any language you want, but we're just to be using Julia for a bit just because it, to me, seems pretty easy to write and read. Of course, if you have any questions, comments, concerns, let me know. I'll totally get to those as soon as I see them in chat. You guys are always great at bringing those up. And again, guys, I apologize for all of the technical difficulties at the start of stream just a little while ago. There was an issue. I agree, Gustron. The one-based indexing has driven me mad at least 3 times now. All 3 on stream, actually. Let's see, back when we were doing the quantum information stuff, the one-based indexing really does kind of screw with my brain a little bit. But that's okay. You know, I wish they would have stuck with zero-based notation, but we'll see how it goes. I mean, honestly, I like the idea of Julia. That's one of the main reasons I'm using it, because conceptually I like the idea. So, let me see here. Yes, okay, good. And there's a few things here that we could have done to speed up the DFT slow and things like that. Yeah, it did a lot of things. We'll see, we'll see. Okay, so let me go ahead and open up Julia over here. And let's go ahead and include Julia test. Oh wait, not Julia test, sorry about that. FFT slow.jl. And let me just do some things here. So, if you guys remember, we can do a time pretty easily here. So let's do x is going to be equal to rand, 1 second, of 1024 elements. Okay, we have 1024 elements for x. Now, what are we going to do? If we do an FFT of x, it does things relatively quickly. Okay, so let's go ahead and time that FFT of x by going back to the start here, home, and doing, I think it's at time FFT of x. Okay, and then up here we see it took 0.0028 seconds. So that's pretty quick. Now, over here we have a couple different functions. We have DFT slow, Cooley-Tukey, and again, this is just kind of the power of the Cooley-Tukey algorithm. I wanted to re-emphasize this because, again, we left off at kind of a weak note last week. If we do DFT slow, which is without using the Cooley-Tukey algorithm, this is without recursion, of x, it takes, obviously, slower time. And, of course, if we time that, give it just a second, it takes almost half a second. So we went from something that took up here 0.00028 to half a second for a slow DFT. Now, if we do Cooley-Tukey of x, hopefully this speeds up. Okay, so this one took, oh, that one actually took longer, but I think it's because we were outputting all this stuff. Let's not output anything. So let me see, where's our print lines? Here, there, and what else do we have here? Print line here, and there. That should be okay. And now let's do, okay, yeah, that one took less time. Although it looks like it still output everything. So I'm not exactly sure why it took less time. Let me try DFT slow one more time. No, wait, let me re-include. Let me re-include the FFT slow. And now let's try Cooley-Tukey of x, and that one took less time. It's 0.048. Yes, good. So that one's slower than DFT slow, which is again going to be about 1 second or half a second. So let's do DFT slow of x. That one took about 0.4 seconds. The other one took about 10 times less time, roughly. So 0.04 seconds. And of course, Julia's native thing takes the least amount of time, which is FFT of x here. Just out of curiosity, could you run Cooley-Tukey with @code warn type? Yeah, sure. So let's see, 1 second. Oh, Cooley-Tukey @code warn type. Code warn type. Okay, let me see. So this is popping up a bunch of errors. I'm not exactly sure what code @warn type does, or @code warn type does. So this is something I'd have to look into. Let's see, tuple array versus line 10. It's saying that we have some issues. Yes, that's something to look into. You guys definitely have access to this code online without too much trouble. So feel free to take a look at it if you're interested. Well, yeah, but I mean, like, yeah. New variable node. I'm not sure exactly what this all means, is my point. So I have to kind of look into that. Anyway, that's okay. So let me go ahead and run a couple of different things here. First, what I want to do is redefine what we have for x. So, oh, I see, and this will give you some of those maybe. Yeah, so the truth is, even though the Cooley-Tukey algorithm is an order of magnitude faster, and will be faster and faster as we move along, the Fourier transform that is going to be used natively in Julia is inevitably going to be faster. And that was kind of my point here, right? Well, one of the many points. The first point is how the Cooley-Tukey algorithm works, right? The second point is that, again, no matter what we do, we're always going to be slower than the native Julia stuff, which is great on the one hand. On the other hand, if you end up having to do something tricky with your FFT stuff, which we might get into in a little bit, you're gonna have to kind of work with it on your own. Okay, so now let's kind of start talking about those different transformations that we were saying before. So first thing I want to do is this. Let me go ahead and use a couple of different guys here. So let me use PyPlot for some plotting. Then let's use images, and using image, what is it, view, I believe? I wrote this down. Pretty sure I wrote this down. Image view, there we go. Okay, this will give me a few things. Load error, dagnabbit. It worked last night. Let me see. While loading TK widget JL, expression starting line 37, image view starting line 14. Hey, angry little bot, what is up? So let me go ahead and control D out of Julia, and let me try it again. So let me do using images. Okay, that should work. Then we're using image view, and let me see if we can figure out what the issue here is. If it pops up another error, let me see. Seems to be okay. Just deprecated syntax and stuff like that. This is another thing that I find kind of weird about Julia. Sometimes it works, sometimes it doesn't. So I think the issue here is that we used PyPlot beforehand, because if you look at this using PyPlot, I'm not able to speak right now, but using PyPlot, you'll know that it'll give us a bit of a warning, but not an error. And that's kind of important here. Recovering from hardware failure. Oh, dude, what happened? I love how your name changed from Happy Little Rat to Angry Little Bot. I'm really sorry, man. What happened? Did like your computer just crash or something? Yeah, and here's the warning. Oh, never mind. Interesting. Never mind, it didn't give me the same warning I was expecting. Okay, so let's just go ahead and go through and do a couple things here. First, let me define x as equal to sine of, let's say, how do I want to do this? Let's do this. We're going to say that x is going to be equal to sine of the following: 2 times pi times I times, one second, I over whatever we want here. So we could say like maybe 5 or something like that. Oops, sorry about that. And let me go ahead and add some spaces here so it's a little bit easier to see. And actually, guys, one interesting thing about Julia that I'll note right here is this right here about how you can actually just do 2 pi. It used to be a feature. I'm not sure if it's a feature anymore. So let's see what happens there. This will be fun. Then we'll say 4 I equals 1 to, let's do 128. Should be okay. Enter. Okay, now one thing that, again, Julia has some really cool things about it that I did kind of want to show off. Let me see. Didn't bother to figure out my password. Motherboard gave up on Friday, only identical part. Is available on Monday. Man, I'm sorry. That happened to me a while ago, actually. Let me see. It was back in college. I had trouble doing some things. Like, let's see, I was writing a report or something like that. And my, I didn't have a hard, wait, what did you say? I didn't have a motherboard error, but I did have some error with a couple errors with some stuff in my computer. The hard drive failed, a few things here. It's just a pain. But it sounds to me like you can get everything fixed. So that's good. That means you probably didn't lose any data or anything like that, which is, I suppose, great. It's just kind of a pain that you have to live without a computer for a while. So let's go ahead and plot this. So let me do 1 second, plot x. Okay, and you'll note that we have a pretty high frequency sine wave going on here. Now, what I also want to do is go over here and divide this by 128. Okay, and now I want to do plot x again, and you'll see, okay, now we have a low frequency sine wave. Yeah, so I saw that. I'm not exactly sure. So the Gusfriend mentioned you can install Arch in Windows Linux subsystem. I'm not sure exactly what the big deal is, because I don't understand the Windows Linux subsystem. I figured you'd be able to install any distribution on that, but I guess just because I didn't understand what exactly it was, I didn't understand that. Yeah, I mean, using Pacman, yeah. It's obviously cool, but I didn't understand, like, could you not install any distribution? Like, you see what I'm saying? Like, is there something about it that makes it so that installing Arch in particular is... you see, it's a stupid question. I know it's a stupid question. I'm just not sure exactly I followed what the Windows Linux subsystem is, and so maybe if you guys could describe that, that would help me out. Okay, so now let me go ahead and plot X, and you'll see we have a high frequency oscillation on a low frequency oscillation. So the idea is we have some big oscillation here, and then a number of smaller oscillations on top of it. And of course we can keep doing this, right? We can say, okay, well, we can do plus equals 1/10 or something like that. And then we have, okay, we have a whole bunch of weird oscillations here. And we can do it again. We can say 1 over, let's say, 64. Now we do plot. And now we have a whole bunch of other weird oscillations. The interesting part about this is if we do y equals, let's do the absolute value of the Fourier transform of x. I think squared is like this in Julia. Let's see. Okay, it doesn't like that. But if we do absolute value of the Fourier transform of here, and then we do y equals, let's do times equals y. Let me see. So it doesn't like that either. Let me see. Absolute value squared. Oh, is there an abs 2? Yeah, there is. Fantastic. Absolute value squared there. And then we plot that. So we plot y. We see really cool things here. So we see the following. Let me see here. And it's marked very heavily being Ubuntu. Oh, I see. So I thought that you wouldn't be able to use anything else. I see. Fair enough. I don't understand what's the problem. There's several free virtual machines, and any of those can run any Linux or BSD or whatnot. Even some come with Nix in a package. I'll be honest, I have trouble with virtual machines. Like, I'm not... How to cancel enter when you insert? Press escape, Spark. Just the escape key. Keep pressing escape. Okay, so here's the interesting part here. We have, let's see, a grid that is from 0 to 128, which is the grid in momentum space, okay? Now, this grid has a couple of different peaks. We have one peak at, let me see, this guy right here, another peak here, another peak here. And these peaks are, well, strategically located at roughly 28. Okay. Roughly, let me see, 28 times, oh, let's see, 28 divided by 2. So this one should be about 14, I believe. Yep, about 14, somewhere in there. And then this one is, let me see, going to be divided by 128, so this one should be about at 1. Okay, so these are our frequency components. We have 3 different peaks, and I realize those peaks repeat on the other side. I'll get to that in just a second. But these peaks right here are related to the frequencies that we just threw into the system. So we threw in a whole bunch of different frequencies. We did 128 divided by 10, which was our 28 here. We did 128 divided by, let me see, 1 second, I have to think here. We did half of that again, which is over here, which is our 14. And then we did half of that, or we did basically one with a single frequency, that is 128. So this is the long frequency that we have, the big oscillation on the outside. Then we have the smaller oscillation, the one that kind of went like this, and the even smaller oscillation still that went super quickly. And these are our 3 different oscillations that we have there. Now, one thing I also want to point out is that we're allowed to do the discrete cosine transformation here. So let me go ahead and do the z, I don't know, is going to be equal to the discrete cosine transformation. We press enter, then you move your line down upwards. You can't cancel this movement. Let me see, 8 Spark Let me see, not working. I mean, when you press enter, then your line moves to down, and you can't cancel this movement. I'm not sure exactly what you mean. So here I'm using VI, which is an older version of Vim, but all of the commands basically work, right? So up, down, left, right moves up, down, left, right. If I press insert, which is I, and I start typing, things happen. If I press escape, I can then move around just fine again. And if I use U, it all goes back. So I'm not quite sure exactly where the issue is coming from, Spark, but it should be that if you're in insert mode, you leave insert mode with escape, unless you're using the interactive mode for Vim, in which case I don't know how to help you. The interactive mode for Vim is I can't figure it out. Sorry about that. So basically, if you're using the interactive mode with Vim, just go ahead and close it right now because that's a pain. But the insert mode, you should be able to leave with escape. Let's see. So when you press enter, then your line moves to down. You can't cancel this movement. And so enter means down. Oh, I think I understand what you're saying now. Okay. You can undo it with U. If you do a command, I mean enter isn't a command, but you can undo an insert with U. Yeah, so I'm pressing U right now, and that undoes the insert. Maybe that's what you mean. Sorry about that. Let me see. AngularBot depends on a CPU, of course. If running some resource hogs, X Windows systems. Yeah, so talking about VMs there. Okay, so what do we do here? If we do DCT of X, we get, well, this plot right here. And if we plot Z, which is our DCT of X, we get something a little bit weird here. Okay? And I'll be honest, this isn't exactly understandable in many different ways, right? So this is kind of why we want to use the FFT instead of the DCT for this particular system. However, I'm not sure what you mean by how to cancel this in insert mode. Sorry about that, Spark. I have no idea because I was pretty sure. So to get out of insert mode, you press escape. To cancel something, which I imagine you're like trying to go back. So I think what you're saying is this. So if you press I and then press enter, it opens up a new line. You just press undo, and that totally undoes that last change. So I think that should be okay. I think it should be okay. Hey, totally not Zuki, thanks for coming in. Okay, so now the DCT looks a little bit different than the Fourier transform, and I realize I'm not being completely honest here, right? Because before, we did the absolute value of the Fourier transform, and then we squared that. So let me go ahead and do this, and then we'll say z times equals. Actually, is there a DCT2? Maybe there is. Let's see. Ab squared is what I want. There we go. And then if we run plot z, we'll see we have this guy. Versus if we do plot y, we have this guy. Okay? So we see we have two clearly different guys. However, one thing I want to point out. Afonso, thanks for coming in, man. I do appreciate it. I apologize if today's a little bit boring than normal. More boring than normal. But I'm kind of getting to something in just a bit. Point is, what we've done here is we've taken all of our frequency components. So we've taken the frequency components of our sine wave and we've compressed them in momentum space. We've found a space in which we can hold all of this frequency, all these frequencies as single, basically delta peaks. And in this way, we have turned our data into a system that we can represent as a sparse matrix. And this is a super important thing. The thing that I'm really trying to drill in, the reason I'm kind of like doing this kind of physical picture and showing you guys this again and again and again, because as we compress or as we work with our FFTs, we can basically transform everything into a new basis. And this new basis, things work a little bit differently. And we can work with the data a little bit differently. Let me see. Good. Okay. So one thing to point out though, is even in the case that we're using the discrete cosine transformation, it's kind of hard to see here, but we do clearly see each of the peaks where we'd expect to see them. So let me go to the DCT again, so plot z. We see three peaks again, 1, 2, 3, but they're a little bit different at a little bit different positions here. So basically we took the real part of the, how do I put this? The real part of the Fourier transform, and we have this. Now, we have a question. At least I have a question. Like what I was saying before, if we take a Fourier transform of some sort of frequency component, right? We can compress that data. In a way, we can put it, let me see. We can put it into a new space where we have fewer components. But the question is, how can we, or how do we know that that representation that we're working with is actually, well, sparse? How do we know that for sure? Well, what we can do is this. Right now we've just been working with 1D Fourier transforms. So we have the frequency components that we're working with. So let's go ahead and work with the frequency components here. So we have X in real space, Y in the Fourier transform space, and Z in the discrete cosine space. So what are we going to do here? First, let's go ahead and plot sort X. So this is real space, okay? And you'll notice that it's actually, 1 second, going the opposite way of what I anticipated. I thought it was going to go up and then down, not down then up. So let me think. How do I sort the other way? 1 second, let me Google this real quick. Sorting Julia. 1 second. Sorting. Let me see. Reverse equals true. That's what I want. Oh. 1 second. Reverse equals true is what I was looking for. Okay, so we'll do this. Sort rev equals true. There we go. Oh, well, never mind. That's not where we go. Let me do real quick. Sort of X. 1 second. Rev equals true. I think it's because I put it in the wrong spot. Sort doesn't exist. Sort does exist. There we go. Now we're going to plot that. Okay, so if we plot that, you'll see that we have the highest frequency values and the lowest frequency values, and they kind of, well, they're kind of ugly looking, right? They taper off kind of funny. Okay, but here's the interesting part. If we do a similar thing with Y, which is our Fourier transform component, we see that they drop off incredibly quickly. And of course, the same thing happens in our discrete cosine. So if we do Z, we see a similar feature right here. And this distinct tapering off is what allows us to do, or what will allow us to basically represent our system as a sparse matrix. And so I've been kind of building up to this in a way, just kind of throwing this out your way, that we have a way of, how do I put this? In order to know whether you can describe your system as a sparse matrix or not, you can actually do so by plotting the components here, the sorted components here. And that's super interesting, because this means we can conserve space on a lot of our different transformations and things like that, or basically store our objects in a compressed form. Now, you can't really see the discrete cosine transformation, so let me try this again, and let me do over here, there. So that was that for the discrete cosine transformation. And you'll see the clear drop-off, like what I was saying before. And that's incredibly cool in my opinion. However, to really see this picture a little bit clearer, let's increase the resolution of X. So we're going to say that, let me see, where were we before? We had all these X's here. Okay, so let's go ahead and define our X to start. Well, I am currently working on FFT stuff. I'm kind of explaining how the FFT works, and then we're going to work on something in just a little bit. Today we're kind of getting all the theory down for basically something known as compressive sensing, which is what we're going to be moving into next. It's actually incredibly interesting, and it's the ability to basically compress data by moving it into another space. So for example, we can move it into momentum space with the Fourier transform, or we can move it into another space with the discrete Fourier, or the discrete cosine transformation, things like that. Lots of things that we can do there. Okay, so we'll say X 128. Let me go ahead and bump this up to 512. And let's say, instead of 5, let's just go ahead and say 512. There. Okay. Now let's go ahead and modify this again a little bit. So we'll say 256 here, and we'll say plus equals there. So we have a whole bunch of different frequency components. And then we'll say 128. Okay, let's see, 64. 32. 1 second, I'm gonna just keep going down for a while. 16. 8. 4. And 2. And finally 2. Okay, so now if we plot x, you'll see we have a very weird looking sine wave. Okay, now if we do the plot of the Fourier transform of x, let's see, abs squared of the FFT of x, we get the peaks that correspond to the peaks that I just wrote in. If we then say that y is equal to abs squared of the FFT of x here, then we plot, 1 second, sort of y, rev equals true, 1 second, forgot a v. We see this drop off here. So we see it starts very high and then it goes down here. This is more obvious in the discrete cosine. So let's go ahead and say z up here. Discrete cosine transformation. And let's change that to z. Okay, now if we do plot z, reverse equals true, we see a clear drop off over here. Now it's kind of hard to see, but if we move it over there, you see the drop off over there. And that's incredibly cool. Again, this means that we can represent our system as a sparse matrix in some form. Okay, so we'll talk about how exactly to do that in the upcoming week, depending on how things go. But this is kind of the heart of it, right? We can see that we have fewer components, and basically, if we cut off like all of the space after this point, we'd be set. There wouldn't even be an issue there. Now, we can do a couple of things here. I had a couple of other things planned, but I think I want to go ahead and move on to... No, let's do something else. So we already have images and stuff read in, right? So let's go ahead and use that. Right now I have an image that I have saved outside. So image is going to be equal to, let's see, load of, and I think I called it ferrofluid. Yeah, that's what I called it, a JPG. And if we do view of image, we get the image that I'm intending to work with. Give it just a second to pop up, which is, it's actually almost exactly how lossy audio and video compression works. Again, we just cut off all the components that we don't need. This is a picture that I took a while ago of my old... Okay, so how do I put this? A while ago I had a YouTube channel where I just put a whole bunch of random stuff on, and this in particular was a picture I took when I did a ferrofluid experiment. I thought it looked pretty cool, and I don't know, I liked the colors on it, so I said, hey, let's just kind of work on this. Work with this. Yeah, it is simplified, but the heart's all there. Okay, so I figured we could work with that image. Obviously, we can view it there. Now, what I want to do is basically grayscale everything. So how are we going to do that? Well, let's go ahead and look at the image. If we take, let's see, image dot, 1 second, height of the image, we'll see that we can find a height and width. So I'm just going to create a new function over here and import it in. So we're going to say function, 1 second, to grayscale image. And basically we're just going to return an array from here that is a two-dimensional array like what we did before. So we're going to say, 1 second, function, and we're going to call it grayscale. There's probably an inbuilt function to do this, but this will be fine. So we'll say image. And then we end the function down here. In here we say for, and we basically go through everything we need to go through. So we will say for I equals 1 to image, 1 second, height of image. I'm just making sure this loop works real quick. Print I, and yeah, okay, so that one seems to work just fine. So we'll do that one. So we'll say for I equals 1 to height of image, and that loop, and we do one for j. For 1 second, j equals 1 to width of image. Okay, end that loop. And then we basically go in here and we say, how we're going to do this, let's just say a of I, j. I don't know if I'm allowed to do this or not. So let me see, a equals zeros. Let's say from 2 to 4. Again, I'm just kind of messing around with things. That seems to work okay. So let's go here and let's say, you can do I and j in one line in Julia. Oh yeah, I probably could. So now let's see, a is going to be equal to zeros of image, one second, height of image, width of image. No, that's not it. No, that's not it, Titsfragger. I'm literally just, I'm describing the Fourier transform, or basically transformations and things like that. As I said just a second ago, we're going to be moving on to a series where we do compressive sensing and stuff like that. It might be just a weekly thing. It kind of depends on how it goes. But for today, I wanted to basically highlight the compressibility of, well, basically all of these transformations in different spaces. That was kind of the point of today's episode. 1 second. We will in just a second. So we'll say zeros here. Aij is going to be equal to... now what do I want to do? I guess we want to add up all of the RGBs together. Basically, this is just grayscaling the image, and then we can go from there. The theory of this type of compression, again, is compressive sensing. I'm sure a lot of you guys have probably heard of it before. But as I said before, the idea is that we transform it into a space that... we transform it into a space where we see that power law decay, like what I was saying before, that incredibly quick decay. And then after transforming it into that space, basically the idea is we do all of our work in that new space so that we can save as much, well, memory or whatever as necessary. It's a little bit more complicated than that, but we'll get to it when we get to it. Give me some time to kind of work with this and describe everything, and then we'll go from there. So we say Aij is going to be equal to basically the sum of everything divided by 3. So we're going to say, here we'll say, if I wanted to grab the image, we could say image of, let's see, 1, 2. I think it needs to be here. 1 second. Image of 1, 2. Yes, and then I want to do dot red. There. So we will say image of Ij dot red plus image of Ij dot blue plus image Ij dot green, and then we divide by 3. And then this should do okay for grayscaling, and then at the end we just return A. Okay, let's write this, and let's go ahead and include the guy. So I think we can just include it down here. Include. That was an M. Include. What do we want to include? Let's do, what's this called? FFT slow. JL. Okay, so we should have grayscale also mentioned now. Now we're going to say A is going to equal to grayscale of image. And we should see, let's see, image not defined. 1 second. Function for grayscale image. Oh, oops, my bad. This is AMG. And this is AMG. Here, there, write this, go over here. Now let's include it one more time. Grayscale. Okay, you seem to not like that at all. 1 second. At index 1, 417. Oh, maybe I did the height and let me see something. I might have gotten the height and everything mixed up. No weighting. I don't know what you mean by no weighting. Sorry about that. Okay, so we'll say and let's go through width first and then height. I think I just got these mixed up. Try including it again. Then we'll say grayscale. Nope, that doesn't seem to work either. What the heck? We're going through all the different elements. Oh, okay, I see. This needs to be changed too then. I never know if things are column or row major. I never do. I can never figure it out. Include A equals grayscale. There we go. Okay, so now we have A as equal to this guy, which is great. It's a matrix, and then we can work from there. So what I want to show, let me see, view of A is this. We now have a kind of weird grayscaled image of our thing. It's not quite right, but that's okay. Oh, okay. I didn't know that, but that's okay. I can take a look at that later. So now we had the image that we wanted to work with. So now I want to do FFT of A. And you'll see that this is going to be a two-dimensional FFT of A. So what I want to do now is I want to do view of the following. Ab squared of FFT of A. There. Okay, so now we see a whole bunch of weird dots all over, right? Completely different than what we saw before. So if we view, let's see, A. Here we see these two images back and forth. And this is kind of what I mean when I said things earlier. We took an image, and again, I just very quickly did a kind of averaging there. I guess not quite grayscaling, but averaging there. We can figure out exactly how that's done a little bit later. But basically, we took this system that was in, basically a weird image, and now we have a bunch of dots. And these dots can be very easily compressed. And that's kind of the idea, right? We kind of move back and forth between these two spaces where we see a whole bunch of weird frequency components here. Now, we can go in more about what the frequency components mean and things like that. However, I kind of want to talk about something a little bit different for the remainder of today's episode. And it might not seem exactly obvious how they're connected to start, but they're definitely connected. And you'll see kind of in a bit. I think in the next 10 minutes as I'm describing, it'll kind of start to make a good bit of sense, but bear with me for just a little bit. So let me go back to Zernal, and let's do page, new page before. He could calculate the color differences. Yes, we could. Sorry, I just did something super quick. We could do it in a number of different ways. Sorry about that. Okay, so now, what do I want to do? Let's start talking a little bit more about this compressibility. Let me see, compress. I think it's an I? Ability. 1 second, is it an I? Let me Google this one real quick. I always get this mixed up anyway, so that's okay to Google. Let's go here, compressibility. Let's grab this, open link, why not? Yes, it is an I. Let me see, Luma video. 1 second. Okay, I'll take a look at this later then. Okay. So, 1 second. Here, compressibility. Okay, so when we talk about compressibility, the idea is that we want to represent things. Gosh darn it, I cannot spell or write at all. Represent data in a basis, we'll say, that uses the fewest points. I suppose that's obvious, right? I mean, like, when you say you want to compress something, that's kind of the definition of compressing. So, in order to do this, I want to talk first about something a little different, and that's going to be norms. Now, I'm sure that Gustorin and Angry Little Bot over there have seen norms before like this, but basically the norm that we typically work with is L2 norm. 1 second. Let's see, x is going to be equal to, or rather, better yet, r is going to be equal to square root of x squared plus y squared. However, this isn't the only norm we can work with. We can work with a bunch of other norms. For example, we could do L1 norm, which says r is equal to x plus y, or the L3 norm, which says r is going to equal to the cubed root of x cubed and y cubed. And to really show what the difference is here, I'm going to very quickly write something up in Julia that kind of just graphically shows the difference here. It's not relevant for theory, except when going much deeper into compression. Psychovisual compression, subsampling of elements, of colors is not important for humans. I don't know what you mean by psychovisual compression. It sounds kind of medieval in a way, but well, psychovisual does. It's kind of like what you psychological torture with visual images of sorts. I'm not really sure. Anyway, my point over here is that with these norms, we can do some drastically different visualizations of lines and things like that. But first, I want to kind of give you guys a pictorial representation of what these norms look like. And to do that, I'm just going to do I'm just going to write something very quickly that, well, basically plots all of the points inside of a norm. So just a very quick Monte Carlo search to show you guys what these norms. I say Monte Carlo search, that's not what we're doing. I'm just going to do a very quick Monte Carlo integration of these different norm spaces, so you guys can kind of see what I mean. So let me go over here. Oh, oops. And let me go back over here. So let's go down here to the bottom, and let's say function to, one second, determine whether a point is inside of a norm, a decided. Okay. Yeah, I mean, I figured that was it, but I'm a little bit confused as to what you mean. So you said it's not relevant for theory, except when going much deeper into compression. Oh, I see. So yeah, I get it now. You're saying that the further we compress the image, right, it doesn't matter to humans because we can't see past a certain level, so to speak. We just can't make a distinction. Fair enough. So now we'll say function. One second. In norm. And what do we want to read in? We want to read in the points value, so we'll read in an x, y, and z. And then we don't need a z here, just an x and y should be okay. And then we want to read in the last thing, which is going to be the power value. So I'm going to say power over here. And then we're going to end here. Okay, so now all we have to do is say if, what can we compress more, as it won't show up as error artifact for humans. Yeah, I think I get it now. Thanks, by the way. Okay, so now we're going to say if, what do I want to say? If, let's see, how do we do powers in Julia? I think it's power of x2. Oh, let's do 2, just to make it a little bit easier. Okay, so how about 2 raised to the 2? Yep, that works. Let's do 2 raised to the 1.4. Okay, seems to work okay. So now we'll say x raised to the power plus y raised to the power all of this raised to the 1 over power, okay, is less than, and what do I want here? Some sort of general radius, which I'm going to say is 1, else, and let's just put parentheses around this just to make it a little bit clearer as to what we mean. And there, we will say return, I think it's capital true. And we go down here and we return false. Let's go over here and very quickly just check true. True. Okay, it is lowercase t. Sorry about that. RGB color space in itself is already a level of psychovisual compression, as we only see the intensity of those few narrow bands in the spectrum. That is fair enough. Let's go here, F. Good. So now we have something that is in norm, and then I just basically want to do function, one second, to basically create array of points to work with. Okay, so now we'll say function, and I'm just going to name it Monte Carlo just because it's super easy here. And what are we going to say? We'll just give it a resolution. Okay. Now, what are we going to do? We're just basically going to create a whole bunch of random numbers that are between, let's see, how about -1 and 1? Sure, that should be okay. So, let's go ahead and end here. And let's go ahead and create all of our random numbers. The parentheses and if are going against the Julia style guides. Are they really? So wait, you want me to have no parentheses around the if? Something like this? Does that work? We go over here. Let me say if x equals 5 end. Okay, well, we'll see what happens. Not a big deal. So now we're going to say for I can simplify it a little bit by returning expression. Yeah, I get that. It's just, I always kind of like, I don't know. It's fair enough. It doesn't matter. I'm finding this so much fun, so much stuff on the internet I didn't know that existed. I feel like that's generally true. People just find things. Yes, thank you, Angry Little Bot. Or Happy Little Rat, or whatever. So we're going to say for, and how about we say I equals 1 to resolution. And we end it here. And basically we say x is equal to rand x equals rand of 1. Okay, I guess we'll say, I haven't needed them to look till now. 1 second. I guess we could create all of the random numbers. I just want one random number. So how about we do rand times times 2. Then we do minus 1. Wait, times 2 minus 1. Yeah, that should be right. Right? Okay, so wait, it's from 0 to 1. We want it from 0 to 2, then minus 1. Yeah, that is correct. So we want rand of 1, let's say, times 2, minus 1. Let me see. You'll have your time spending problems solved if you dive into this. I mean, not surprised they do, but I haven't need to look at them until now. Yeah, so here's the thing. Sorry to get on a little bit of a sidetrack, but one of the people at my university, and I like this guy, he's a good friend of mine, times 2 minus 1. Basically, he said something rather interesting. He said that, let me see. He said that he doesn't like the internet very much. He was saying that he doesn't like going on the internet very much and things like that. And he was saying that like the internet is this loudness war where people constantly scream at each other in order to get people's attention because they want to basically live on the internet, if that makes sense. Like they want their entire world to be the internet. You know what I mean? And the issue here is that though I do kind of agree, I do see a lot of people like struggling for power on the internet, you know, like especially on YouTube and Twitch and things like that. And even clickbait articles you find on Facebook. I find that true too. For me, the internet is huge. It's like, again, the entire sum of human knowledge basically available at your fingertips. And to say that you are, I don't know, that the internet is somehow just a bunch of clickbait, or the internet is a bunch of trolls, or the internet is a bunch of, I don't know, something like that. I feel like you're discrediting it, you know? Like, I can't remember the last night I wasn't, I can't remember the last night that I wasn't like on reading some paper I found from the archive, or browsing Stack Overflow because I couldn't figure out how to fix an error, or on Wikipedia trying to understand something new. Like, that's just what I do. And I don't know, I feel like it kind of hurt my feelings a little bit when people just said, anyone who spends all their time on the internet is like a loser, basically. They were saying that, you know, you're wasting your time. And I'm like, no, I'm learning things, you know? I thought it was cool. I just wanted to hear you guys' opinion on it, I guess, because I don't know. Like, to me, the internet is a place I go to get things, and I get a lot of things off the internet. It's super cool and fun. It's enjoyable. But I guess if you're using the internet just to waste time, it's not quite the same. Anyway, that was just kind of a side topic there. Completely off topic, I finally managed to recreate the database scheme for my Japanese learning tool. Oh, super cool, man. I don't want all this information in printed form on the shelf somewhere. I could imagine. Actually, you can print out versions of Wikipedia, can't you? Right? Isn't there a way like you can print out? Maybe I'm wrong. Like the Wikipedia encyclopedia, I thought was a thing. Okay. Now let's go ahead and read X and Y into our system. So we created rand of 1. But here's what I actually want. Rand of 1. And then I want the first element of that. Yeah, that's actually what I want. There's probably a way just to create a single rand. Let me see. X equals rand. Oh, okay. So forget the 1, and then we're set. Now what we want to do is, in here, return. Better print it at work. Yeah, that way they have to pay for it. So then we're going to if in norm, and we're going to give it a norm value, which we're going to say is, let's see, x, y, and I guess we'll say power here, and we'll read in power too here. What are we going to do? We need to append, oops, end. We need to append something. So we basically say, let's see, what is it? X dot append 2. Are we allowed to do that? Let's say x equals array of 0, 1. Wait, I got this. Let's say x equals the following. Okay, now we say x dot append 1. Array has no field append. Push back. Dang it. Okay, wait, I need to look this up. Let's go through here. Appending array Julia. Let's see what we got here. Learn Julia in Y minutes. Array. Append. Push. Is it push? Let me see here. Append. Append. Push. Oh, wait, what? I feel like this isn't what I want. Is it what I want? 1 second. I gotta figure this out. It's push, exclamation mark. So you're saying... Wait, this could be a number of things. Nope. So we'll say push, exclamation mark, x1. Okay. Okay, there we go. That seems kind of weird. But that's perfectly okay. So let's go up here and let's say array is equal to this. Sure, that's okay. Then we'll say push, exclamation mark, a, and we want x and y as a single point. So, 1 second. X and y as a point. Yes. So then we want to do this. So let's say a equals the following. Oh, 1 second. What is your favorite science book of all time? Simuleos. Push, exclamation mark, exclamation mark. Oh, is it 2 exclamation marks? Wait. The function mutates the argument. My favorite science book of all time. I'll be honest, I am partial to Griffith's Electrodynamics. Like, I really like that book. It's great. It's great. What I don't like is that it's not enforced. I see. Okay. One thing I have to think here really quickly. We have to put this into an XY array. Okay. So I actually want to do the following. Let me see. If we do A is equal to this, and then we do push A, 1, 2. I don't know if we're allowed to do this. 2 element array. Yeah, so what I want though is not, I want 1, 2. No. What if we push an array or a list of this? Is that allowed? Okay. This is probably a stupid way to do it, but let me do X, Y. Oh, what was I trying to type there? X, Y? Here. Okay, so this will create a list of lists. And then we're good. And we just return A at the end. Let's go down here and let's return A. Man, I feel like... I wanted a 2-dimensional array though. Let me see. Okay, so now let me go ahead and include it as before. So include fft slow.jl. Okay, syntax in separator tuple. Let me see, what do we have here? 77. It says push a x y. An expression starting at line 77. Okay, it doesn't like the push. Let me see, why would you not like the push? Let's try it again over here. A is equal to this. And then we're going to do push, exclamation mark, A 1 2. Seems like that okay. You're fine, Angry Lobot, no problem whatsoever. Let me see, why does it not like the push? Is that not exactly... Okay, so let me see. It doesn't like it though. So we'll say Rand is... Oh, I bet you I know why. What if we do... No, that's okay too. So how about this? Let's just print it out real quick. So let's do print line of X. We would just print one out. And let's do include. It still says we have a problem, but that's because I didn't write it. Oh, you still have a problem. Extra parentheses in the F. Oh, okay. Now let's go down here. Sorry about that. And let's do push exclamation mark of the following. So we'll say A and then X, Y. There, let's go here. Now let's do include. Okay, it seems to work okay. You mean enforce like in lists? Or what do you mean by enforce? Overall, I really like Julia, but some implementation details just don't agree with me. Yeah, that's generally what I think too. Like, I love the idea and concept of Julia. I really do. I think, given time, it will work fine. But for now, there are a whole bunch of weird things that just, they do strike me as kind of weird. So let me do real quick, Monte Carlo. I will say A is going to be equal to Monte Carlo of, what do I want? Let's do 100 and let's do 2. Okay, now I want to do plot of A with RO. Invalid character literal, RO. 1 second, plot A. Okay, that wasn't quite what I expected. 1 second. I have over here that we should be able to plot. 1 second. Let me see. Let's do plot X there. And I want to do 1 second. RO. Okay, you don't like that at all, and I'm not exactly sure why. So let me go over here and Google it again. PyPlot, two-dimensional plot. 2D dot plot. Let me see, shapes and collections, PyPlot. Should be okay because we're using PyPlot, right? So it should be that plot. Let me see, what do we have here? Oh, those are histograms. I just want a dot. That's literally all I want. A dot at a particular position. 1 second. 1 second. None of that. That's kind of silly. Come on. All I want is just a single dot. Just clicked on the same link. I want a dot. This is what I want. Right there. That's it. Okay, so how do I do this? They say that if I do a plot here, this should work. So let me try plot of this guy. Let's go over here. Oh, oops, my bad. Invalid character literal. Okay. Uber Wachu, amazing. Thanks. I don't know what you're saying is amazing. But oh, you're talking about the Rust thing, probably. Okay, so for some reason, and this is completely unexpected, PyPlot doesn't seem to work the same way in Julia as it does in Python, which is great. So let me go over here and let's figure this one out. So let's do PyPlot, Julia, and let's see, plotting for Julia, plotting examples using PyPlot. Okay, let's see what we got here. Basic plot, plot annotation, time, subplot, polar plot, histograms, bar plot, error. I just want a scatter plot. There we are. That's what I want. Where are you? Scatter. X, Y, S, area, alpha. Good. Okay, so we'll do scatter of A. Didn't seem to work. Okay, so let's grab one column of A, which I think is A of, let's do one here. Array of 2. So let's do it the other way. So let's do colon first, then 1. Okay. So let's do let's do A of 1. Okay, wait. A of 1 is the first column. We do 1, 1, we get that. Okay, so what I want is this. Nope. This. Nope. I want all of the X components. So, nope. 1 second. A is that. So we have all of these guys, 78 elements with 1 element in it each. So what if we do A? And we want to grab all the elements. So let's do 1. Okay, and then we do 1 again. Dang it! I thought this would work. Okay, I need to find a way. Gosh darn it, how do we store it as a 2-dimensional array then? We want to push back X and Y. Is there? Let's see. The problem is we stored it as a list of lists instead of an array. This was supposed to be super, like, okay, so you want to do, let's do dim A1. Okay. Let me see. List of list, Julia, let's Google it. List of list, Julia. What do I want to do? Let's see, arrays. Let's see. VCat should be okay. HCat. Dang it. Okay, what do I want to do here? I have to think. Okay, we have a list of lists with all of the X and Y components. That's good. A list of lists with all the X and Y components. Now, what do I need to do? What I need to do is pull out all of the X components or the Y components so I can do a scatter plot. So, let's see, how would I pull, if I want to pull, let's see, 1, 1, 2, 1, 3, 1, fine, let's do length of A, okay, 78, so that's not right. Oh, maybe it's right. Sure, okay, that's fine. I don't know how to start a 2D array, so I guess we can go here and we can look. So let's do 2D array, Julia. I couldn't figure out how to work with the 2D array here. I just need to constantly push back elements in the 2D array. So we'll do... I guess we could set all the elements we don't need to 0. That's fine, I guess. Let me think. So what do I want here? Let me do push back. Dagnabbit. Pushing to 2D array, Julia. I just don't think it's a trivial thing. Multi-dimensional array. Let me see. What do we have? Excited to see other solutions. A array ones D push A B. D1 equals 10, D2 equals 10. Ones, D1, D2, HCat, A. Yeah. It's easier just to do it this way, I think. So let me just do this. So let's do 4. I think we need to return X and Y anyway, right? So let's do 4. I equals 1 to length of A. X. Oh, dagnabbit. So we're going to say X equals this. Y equals this. Then we go up here and we'll say 4. I can't find it anymore. That's fine. 4. What is I equals 1 to length of A. And then we're going to do push exclamation mark X of, and what do I want here? I guess we will take A of I1 and so now let's take X. Good. Now we do the same thing for Y. 2. Okay, so now we should have x and y. Let's just do x minus y to make sure they're not all zeros. Good. Now we're going to do scatter of x, y. Okay, there we go. We have a scatter plot. Finally. Okay, so what I want to do then, let me see, is the following. So let's return, let's do x comma y here, and let's just do the following. So we're going to say for, what do I want here? I equals, to get x from a list of lists, you can do map a x to x1. Let's see if that works. So let's do map of a x pointing to x of 1. Start has no method start. So let's do 1 to length of a, and then we're going to say, let me go up here and just do x equals that, y equals that, and let's go here and we'll say push of, 1 second, exclamation mark x, and what did I do before? There we are. A I 1. We're gonna do push exclamation mark y a. This will work for now, and then we'll do return xy. Okay, so now let's do x comma y is going to equal to Monte Carlo of, let's do 1024, just because I like powers of 2 and power is 2. Okay, now let's do, oh, oops, my bad. Let me first include it again. Include, 1 second, FFT slow. Now let's do xy is this. And now let's see what happens. Write this. Let's do a scatter plot. Okay, good. Oh, yeah, the order backwards? Yeah, that's fine. Let me take a look. So let's do, I think we still have an A. Good. So we want map A x onto x1. Start is no method matching start. Wait, maybe it's A x. 1 second. A. Okay, wait, whoa, but those are all 0.313s. That did something. I'm not exactly sure what. So let's just go ahead and do the XY again like we did before, just because I'm pretty sure that one works. So we'll do XY Monte Carlo, and then we'll go ahead and plot that with a scatter plot. Okay, so you'll note that this is a pretty nice circle. You wrote the correct version. What? Okay, but 1 second. That is exactly what I wrote down a second ago. Map. Oh, x onto x1. Okay, I see. Weird, because I thought I tried that. Okay, so now let's just add that in here then. So we will say, 1 second, x equals, I guess we can do it this way. Let me see. So let's do this, and let's just do variable z. Now let's do z, just to make sure it mapped. No, okay, so it didn't do that. So what do I need to do? I need to say z equals that, and now z. Good. So we'll say x is equal to what we just had down a second ago. There, so we'll say x equals map. 1 second, x onto x1a. And we do the same for y. Y onto 1 second, y1a. We can probably remove these guys now. Write this, go over here, do the last include, wherever that one is, there we are. And let's do xy equals Monte Carlo. Now we're going to do the last scatter, here it is. Oh, I know what I did. This needs to be a 2. Now let's try that. Include, xy, scatter, Okay, good. Now we have our circle. Point was, after that we have a circle. Okay, let me try it again with quite a few more points. Let's do 4096. And let's do scatter. Okay, clearly we have a circle there. Now, if we change this power of 2, we start to see different things. So if we do 1, we should see a square. But we don't, which means I did something wrong, which is okay. Okay, 1 second. So that means I'm doing something wrong here, up in our guy up here. So let me see. X to the first power, Y to the first power. It is working up in the upper right-hand corner. So let's do... Let me try something then. Absolute value of X. And then we do here, absolute value of Y. Let's include it one more time. And then let's do XY and scatter. There we go. That's what I wanted to see. No, this is exactly what I want to see. Okay, so this is the difference between the norms. Now let me do 3. Actually, let's do 10. And now let's do scatter XY. Good, good. Exactly what I wanted to see. And finally, let me try one more thing. Let me try 0.5. And let's do scatter. There we go. Fantastic. Okay, so guys, the reason I did it this way is simply because it's kind of easier for me to see, although I understand it may not be easier for you guys to see here. That's perfectly fine. Point is, the L2 norm is exactly what you would expect. The L2 norm is x squared plus y squared. So when we do a scatter plot of this, we get a circle, right? Because the length at any given point in time, x squared plus y squared, and that's exactly the radius of a circle. Now, obviously, if we do an L1 norm, which is simply Lx plus y, we're going to see something that looks like a diamond. So if we do the L1 norm here, we get a diamond, right? Okay, and as we increase the norm to higher and higher values, basically infinity, so if we do, let's say, 1,000, and we do scatter that, we get basically a square in the other direction. Okay, so now you might be asking yourself, what is the point in all of these norms? It's actually incredibly related to what we were just talking about before with the compressibility. And I'm going to kind of describe this in a bit of a weird way in just a second. However, I kind of wanted to show you guys what these norms are because it's incredibly interesting to me. So again, if I go to 0.5 and I do a scatter plot of that, we see this diamond shape, like what I was saying before. And the idea is, well, basically, we have different different ways of representing a unit sphere in each of these different norms. So the unit sphere in our typical case is the L2 norm, which looks like this, and it is our unit circle. In the L1 norm, the unit circle is actually a diamond. So here's our unit circle there. 4-pointed star, sure. That's exactly what it is. So as we drop down further and further, we get to exactly what Angry Little Bot's saying. So if we do 0.5, and we get to a star in here. Wait, is a 4-pointed star supposed to mean something? If it is, I apologize for that. So now let's do scatter here, and we see this star kind of appear. Now, of course, as we get higher and higher, it changes too, and we can talk about that in a second. So now let's do scatter that, just to kind of show what I'm talking about here. Now, I realize this is a lot of effort for very little gain, but let's describe exactly what we're talking about here. New page before. Okay. So, my back is hurting. We've got about 10 minutes left in today's episode, and we got most of the way done with what I wanted. I realize it doesn't look like we did, but we really did. Again, this is kind of a primer for what to think about in the last case. That was the L1000 norm. Let me go over here and replot it. L1000 norm, so it's x raised to the 1000th power. Let me pop it over here and just kind of leave that up for just a second. It's basically just a square. This is just a square. The aspect ratio is weird. I'm not sure exactly how to fix that in PyPlot, but it is just a square. It looks like a rectangle, but it's a square. Yeah, right, Galvabar? Like, this is super cool. And I guess I just didn't know how to do this in any other way. Okay, so let me talk about the norms one more time. Okay, so L2 norm. The unit sphere is a circle. So let me just go ahead and draw a circle. Okay. Then we have L1 norm, which in this case is equal to a kind of sideways square. Okay. The L0.5 norm, which we saw before, looks something like this. Oh gosh. Let me see if I can redo that. Something like this. And the L1000 norm looks something like this. Okay? So we have these shapes, and I apologize for not being able to draw that star for the L0.5 norm. However, you could imagine taking this L0.5 norm and going to an L0 norm. And in this case, you could imagine that we have basically just the axes here. Oh yeah, they're everywhere. Okay? So here's kind of a way to physically depict these pictures, or physically think of these norms, right? So this is equal to, let's see, let's do it here. Square root of x squared plus y squared. Okay? This is going to be x plus y. This is going to be, let's say, 1,000th, x to the 1,000, y to the 1,000. And this 0.5, let me see, it's funny how useful even in generating graphics or emitting particles. Yes, so then this guy right here is going to be square root of x plus square root of y squared. And this guy is something raised to the 0. No. One second. Something raised to the infinite, and then something raised to the 0, and something raised to the 0. Point is, it's basically the axes. Okay? So, here's why they're interesting. If we do page, new page before, oh gosh, I don't know the best way to describe this, so forgive me if this is a little bit hazy. But let's say we draw a line. So let's kind of draw an axis. Here, I'll draw them all straight lines. One here, and one here, okay? Now let's draw a line that kind of crosses here, okay? Now, let's imagine we're trying to represent a single dot on this line. If we want the closest approach, we use the L2 norm, right? And this will give us a circle that touches the line over here, okay? And so then we'll say, okay, that means that we have a point that represents this line right here. Good. That's one way to do it. However, this point is, we'll say, because I'm not very good at estimating here, we'll say 0.5x and 0.5y. Okay? And our unit circle is quite large. Okay? Now, if we represent this system in a different subspace, in a different space entirely that doesn't use the L2 norm, but instead uses the L infinity norm, then we have a square that looks something like this. And in this case, the difference, ooh, that doesn't look like what I wanted it to look like at all. We have a square here. Something like this, okay? In this case, the square is smaller than the circle. We have basically the same representation of 0.5x and 0.5y. That's perfectly okay. But we've used a different shape. We've used a different, how do I put this, representation of space. And if we go back to the L0.5 norm, we have something incredibly interesting. We have a completely different point that represents this line. And that point will be maybe up here as 0 in x and 1 in y. Okay? Now, all of these guys are valid dots on this line, right? So no matter what norm we use, we will find a dot on the line. The question is which dot uses the least number of dimensions? And that is clearly the L0.5 norm, which I just put down. In fact, we have this thing called L1 minimization. You could do L0.5 minimization or L0 minimization. That's perfectly fine too. The idea is that if we have that line in space, like I said before, maybe something like this time, we basically just grow a diamond at the center. Here's our diamond. And we continually grow it over and over again until we eventually hit our line. Wow, that was a very bad representation of that. Until we eventually hit our line. So something like up here, down here, down here, down here. Okay? And then we have, I was expecting that to be higher. Let me try this again. Okay, that looks better. And we'll see the points here. Okay? Because we did L1 minimization, and the L1 diamond is always along the XY axes. No matter what we do, well, assuming we're hitting a line, we're always going to hit the line along an axis, which means that if we minimize along L1, we will always have a smaller number of points to work with in the end. Okay? It's not a perfect system. You're totally right, Angry Little Bot. And this is something I kind of want you guys to think about. Okay? And I need to think about it too, right? I mean, this is kind of the heart of compressive sensing. The idea is that we find a transformation that allows our system to live in L1 or smaller, right? Because you could imagine smaller, the smaller L is, the better representation we have, or the more compressed representation we have, right? And what we're doing here is basically very similar to what we were doing before with those transformations and seeing them decay with the power law decay. Their relation is kind of hazy right now, I realize, because I didn't do the best job of describing it. In fact, I'm not sure if I fully understand it as well as I could, but this is another situation where, you know, I'm kind of learning this with you guys, and this was super cool. I went through it this weekend, and it's incredibly interesting how we can do this minimization stuff. In fact, I'm running into a situation at work where I really need to do something with the system that I'm working with to compress it, and I want to try to use compressive sensing for that. So I want to learn compressive sensing here on stream with you guys, see what we get. Now, as far as today's stream is concerned, I think we're at a point now where we did the different norms, and we've showed the different unit spheres in the different norms. If you want, I can show that again. Just let me know in chat. But I'm going to go ahead and put this code up on GitHub so you guys can see it. So let me go ahead and right quit, do git commit fft slow .jl, and I'm going to add in a message saying adding in Monte Carlo visualization. One second. Let's actually just put the plotting into the function, just so that we don't have any ambiguity here. Let's go down here, G, and let's say we return X and Y, but before we return X and Y, we're going to say scatter of X and Y. There we go. And in fact, we don't even have to return X and Y in this case. Let's go up to the very top here, and let's say using pyplot. Okay. Right, this go over here. Let's include it. Where's the last include? 1 second. I know it's up here somewhere. There it is. Include. Okay, now let's do Monte Carlo of, let's say, 1,024 points, 0.5. And this should go ahead and plot it. Okay. There you go. Using pyplot, everything should be set. Now let's commit it. So git commit fft slow message, adding visualization of Monte Carlo. Let's say Monte Carlo visualization of LP norms. So then we'll do git push origin master. And now you guys, oops, origin with an N. And now you guys have access to the code that we worked on. I've come up with this by name of sparse sampling more often in my field. Yeah, so it might be called different things by different people. The one that, the guide that I've been kind of going through is the following. So let me see, compressive sensing. It's super cool, guys. Let me see, compressive sensing, an introduction to compressive sampling, maybe? Let me see. I have it right here. Oh man, I did back and buys yesterday. My back is killing me. Ugh. An introduction to compressive sensing. This is it. So I will give you guys a link to this as soon as it loads up so I can make sure that it is correct. No, this is not it. Dagnabbit. It's by the same name. Introduction to compressive sensing. Oh, that's sampling. Sensing. Let me see. Introduction. Let me see if I can find it for you guys. Introduction to compressive sensing. It might be... No, it's not this one. This one. Now I'm just clicking random links. This is not what you should do. Mathematical introduction to compressive sensing. No, it's literally just an introduction to compressive sensing. That's the name of it. One second. An introduction to compressive sensing. The actual compressive sensing comes from something else. So the sensing itself, maybe it's this one? Polynomial matrices. Let's see, what's this one? Oh, this is it. This is it. Found it. Good. Okay. So whatever this one is, that's the one I'm working on. Good. Okay. So that's kind of what I've been working off of. It does a pretty good job of going through everything in a little bit of a mathematically intensive way, but I like that. We're going to be going through this with my friends at work. I guess workmates. Oh, they're friends, right? I don't have any real friends, so workmates are friends. No, they're friends. They're friends. Anyway, point is, I'm going to be going through this there. The actual sensing comes in from sensing matrices. The idea is that we automatically detect the system in a compressed state. But it kind of is related to the... Oh, did it not work? I'm sorry. I just realized. 1 second. My bad. Where to go? I'm sorry. 1 second. An introduction to compressive sensing. Let me look that up again. Let me try it again. To compressive sensing. It downloaded it as a PDF and I just gave it to you guys because I wasn't thinking. Introduction. It has to be this one. Yeah, it's that one. Okay. This is the one I want. Okay, so let me copy link, address. 1 second. Here. 1 second. Ztoko, is that what you worked on today is compressive sensing? Yes. See if that one works, guys. So yes, Ztoko, that's basically what we did. We worked on the principles behind compressive sensing. So we talked about two things. One is power law decay. When we change into, like, let's say an FFT or a, what do we call it? Cosine transformation, so discrete cosine transformation. We see that power law decay of the necessary elements we need in our subspace. And the other thing, yeah, I've got a friend who's got like a million Chrome tabs up at a point. Anyway, guys, the other thing we mentioned was, of course, the L1 and all the different norms, the LP norms as they're called, which is, by the way, super cool. I just want to point out how cool those norms are. For me, as someone who always thinks in the L2 space, I always think of circles, you know, so whenever anyone says a unit sphere or unit circle, it's always a circle. But with these L norms, they aren't just circles, they're diamonds or squares or weird little pointy things, and it's super cool. Basically, with compressive sensing, this is the pointier L is, the better it is. And that is it for today, guys. I know it might have been a little bit scattered. That could have been because we were doing scatter plots, or it could have been for a number of different reasons. Yeah, L1 regularization is similar to what we're going to be doing. L1 minimization is maybe what we're hitting next. So I have three other things actually I want to hit this week. And I will see you guys again on Wednesday, my time, which will be Tuesday afternoon your time. So there's 2 or 3 things I want to do. So one thing I want to do is I want to go through a detailed, how do I want to put this? I want to go through a detailed guide to GDB, the new debugger. Another thing I want to do is L1 minimization, which again is the heart of compressive sensing. We'll get into that in a second. And then what's the other thing I want to do? Oh, I finally got the color quantization stuff working kind of sort of over this past weekend. Figured out what the bug was, fixed that. So now we have to do the tree culling in that, which should be a lot of fun. So we'll see where that goes. Ultimately, I'm liking having a little bit more time preparing for these simulations. They're great. I enjoy having that time so that I can actually like look up this kind of stuff on the side. I mean, I spent the entire weekend learning things for stream. It was actually quite enjoyable. But we'll see how far it goes. Again, let me know what you guys are thinking about the stream, anything like that. Again, tomorrow I'll take the day off and then we'll come back the next day for the next episode of Simuleos, where we do a number of different things depending on how far I am preparing the next, I guess, episode. So we'll see how far that goes. Anyway, guys, thank you so much for watching. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, which will be Tuesday afternoon your time, Wednesday morning my time, where we do some more cool stuff. Thanks again, guys, so much for watching, and I will see you next time. Bye, guys.